So good morning, good afternoon, good evening, everyone. Thank you for joining us today and welcome to this Community Near Fault Observatory breakout session on spatial variations of rock properties and deformation processes across rupture zones. I'm Casey Adderhold, Project Associate at Incorporated Research Institutions for Seismology. Real quick, IRIS is committed to fostering the exchange of scientific ideas by providing a safe, productive, and welcoming environment. All participants today are expected to abide by the IRIS meeting code of conduct, which has been posted in the chat. Geophysical data collected within rupture zones of significant earthquakes are essential for testing and developing further models of earthquake processes. Focusing on in situ observations in the immediate vicinity of fault zones, where rocks suffer permanent deformation during faulting events, could transform the understanding of earthquake physics, improve ground motion prediction estimates, and contribute to structural engineering efforts to mitigate earthquake impacts. This breakout session is one in a series of sessions intended to gather input from the broader earthquake science community on key research areas, science questions, and the data and experiments needed to address them in the near fault zone. This breakout session will be recorded and archived on the IRIS Earthquake Science Presentations YouTube channel, and the discussion held here today will inform future sessions, workshops, and proposals. Should you have a comment or question as the session unfolds, then please clearly and concisely type it into the chat box on your Zoom control panel. If you would like to ask a question or make a comment, you can also raise your hand and we will call on you. At the appropriate times, we will read your name and question to the presenters. If similar questions have been asked, we may combine or skip them. If the session happens to crash due to Zoom or internet issues, we will reboot it. Just click the Zoom link again. And automatic captions are available to be turned on and off on your Zoom control panel. To get an idea of the group we have here with us today, I'm going to launch a quick poll. Please go ahead and select your career stage and the type of institution you are currently employed or enrolled in, and we'll go ahead and share those results so that everyone can see. You should be able to see that coming up here now on your screen. No worries if you don't, but you should probably update your Zoom if you're not seeing a poll. So I'll just give it a couple seconds here. Thanks so much. If you're joining us, we're just doing a quick poll. Right. And we got 80% participation, so go ahead and show you the results of that really quick here. So you should be able to see now the results. Looks like we got a good mix, maybe not so many recent grads, but they're probably pretty busy, but mostly academics and government. That's great. Nonprofit. Great. All right. So I'll go ahead now, stop my screen share and pass this to Ashley Griffith, Associate Professor at The Ohio State University, to present an introduction and to moderate the rest of this session. And if you want to go ahead and share your screen there. Perfect. We'll do the poll at the end.
All right, great. You seeing this, Casey?
Yes.
All right, great. So welcome everyone to this breakout session on spatial variations of rock properties and deformation processes across rupture zones. I'm convening this along with Ramon and Arrowsmith, who you'll hear from shortly. This is the first of 4 breakout sessions on different topics, all focused on identifying key processes, signals, observational technologies, and workforce development necessary to optimize a community near fault observatory. For those of you who are attending this breakout session and are new to the concept of the community near fault observatory, I invite you to take a look at the short opinion piece on the topic that was just published this month that's shown in the bottom left-hand side of the screen. Yehuda Ben Zion and Greg Barroza, among others, were authors of this paper, as well as the information page hosted by SCEC. There's a link in the bottom right-hand corner of this slide with YouTube links to a number of talks on the subject that were part of a Rupture and Fault Zone Observatory workshop held in 2021. So in this particular breakout session, we're interested in linking near fault geological observables to key processes involved in the pre-SYN and post-rupture process. So just a few things to keep in mind. I'll talk about the structure of this session here in a second, but just a few things to keep in mind as the session proceeds is there are some key scientific questions that we're really interested in, including what do we see geologically and geomorphologically when we look across fault zones? Are the things we're looking at shear-related products, volumetric products? What are the implications of these products, and what is the time variability of the signals that they represent? How could we observe these using a purpose-built observatory, and what do we need in the observatory to do so? And in the context of these scientific questions, we're interested in the signals that inform us about the science questions, the properties of the observatories that are required to record these signals, and how we can involve the next generation of scientists and train them to become involved in the observatory and the data that's coming out of it. So the structure of the section is as follows. For the next sort of 30 minutes, we're going to have 3 brief presentations. Ramon will introduce each of the speakers as they come through. And these speakers will, I'm sure, motivate lots of discussion and questions. This will be followed up by a 45 to 50-minute Q&A and discussion. And there are lots of ways to interact with this discussion. So you can raise your hand and submit an oral question. You can submit a question via the Zoom chat tool that, as Casey talked about before. And there's a third option for people who run out of time or don't want to talk out loud, that we're going to maintain a Google Doc page. The link is here. This is not very useful, I understand, to you. So after I'm done talking, I'm gonna paste this link into the chat so you can click it. And it's formatted where you can leave your name, contact information if you want, and any sort of comment, discussion, thought relevant to the questions in the session. So with that, I will pass it on to Josie to share her screen and Ramon to introduce.
Yeah, so thanks everyone. Thanks to Casey for getting us going and to Ashley for starting the introduction. I just a couple of quick points is I think the ambitious view that was articulated by Yehuda Ben Zion in his opinion piece and is consistent with what we need. We need to take this quantum leap in our ability to observe fault zones so that we can have a quantum leap in our understanding. And this is the opportunity. And then the other point is, the success in this activity will come from us all working together to really clearly articulate the questions and the opportunities. And so that's why we're here, and that's why we need everyone's help to put some ideas out and even write them down in the Google Doc. But also we need to have this authentic community engagement. We want to invite people to be part of this effort, and so that's what we're doing here. So let's begin. We're really grateful to our speakers for their agreeing to present on fairly short notice. And so our first speaker is Josie Nevitt, and representing her colleagues from US Geological Survey and beyond. And she's going to talk about mechanical factors affecting fault slip near the Earth's surface.
All right. Well, thank you for the invitation. And I'll start by just acknowledging the large group of collaborators who all contributed to the work I'm presenting today. And I'm presenting a combination of published works and work in progress. So when I think about fault and rupture zone processes, I think about the various factors that can be affecting the temporal and spatial distribution of fault slip. So that includes lithology, water, frictional properties of pre-existing structures that can affect the orientation relative to the background stress field, mixed mode fracturing to actually reach the Earth's surface, structural complexities, plastic yielding within the fault zone, and changes in the elastic moduli. So I'm going to touch on most of these topics today, but I'm really going to focus on these 4 and using these 3 case studies. And so I'll start with the South Napa earthquake and thinking about variations in frictional properties and the effect of water. So the South Napa earthquake nucleated about 10 kilometers depth and propagated up dip towards the north, kind of hugging the base of this alluvial basin. So geologic observations of co-seismic slip were really confined to the bedrock unit at the surface, and then post-seismic after slip accrued in the alluvial basin to the south. And so we're studying, or we have been studying, the deformation signals both within the co- and post-seismic portions of the rupture. To very briefly summarize our previous work, we used mobile laser scanning of the deformed grapevine rows, along with elastic modeling to infer a very shallowly buried rupture tip, and that slip at depth exceeded that which would be observed at the surface. And this was true both co- and post-seismically. We built on this study using active source seismic imaging and elastoplastic finite element modeling. And what we found was that both the slip distribution at depth and the deformation observed at Earth's surface was relatively insensitive to the inclusion of a compliant zone around the fault. So that's this blue stippled model compared to the homogeneous elastic model, which is a solid blue line. We also found that, that in order to fit the geodetic data, the modeled slip distribution needed to have this high slip gradient at the fault tip, and that this was only permissible by including plastic yielding in the material. For our 2 study sites characteristic of either the co- or post-seismic surface deformation, we built forward elastoplastic finite element models that were based on the site-specific mechanical properties from the seismic tomography and fit to the geodetic data to infer the rupture tip burial depth. And so this was 10 meters at the co-seismic site and 5 meters at the post-seismic site. And so this question of why the rupture would stop so close to Earth's surface and how you get a reduction in shallow slip has really motivated a lot of our subsequent work. So we drilled into the fault zone at both sites, hitting the principal slip surface at the post-seismic site, which is shown here, which confirms that there is actually a buried slip surface at depth. It also provides direct observations of this distributed shearing, which is consistent with the frictional plastic yield criteria used in the models. We also are able to measure directly the depth to the water table, which is shown as these blue squares here. And we see this pretty striking coincidence between the water table and the inferred rupture depth, which were determined completely independently of each other. So this motivated a series of saw cut friction experiments to look at the effect of water on the frictional strength of these fault zone materials. And so we saw that these fault zone materials are almost twice as strong when they're dry compared to when they're wet. And so we should expect for terrestrial faults that the very shallowest portion of the faults that are unsaturated will be frictionally strong. So now we're going to move on to thinking about interseismic creep along the Hayward Fault. And so although this is not earthquake slip, it's related to the Napa study by the importance of water and the frictional properties and a shallow slip reduction, which we're able to observe using in situ borehole observations. So our study site is the historic Gallegos Winery, which is located in Fremont, where the creep rate is about 6.5 millimeters per year. And an advantage to studying creeping faults is that you get this reliable geodetic signal and can learn about fault processes in general. So the site includes a creep meter and 2 boreholes. And what's really exciting here is that one of these boreholes crosses through the Hayward Fault at about 20 meters depth. And so we're able to use an inclinometer instrument to measure the borehole deformation at depth and compare that offset with the surface record from the creep meter. So this plot on the left in red is showing the borehole fault parallel displacement with depth. So you can see this zone where it's being offset by the fault. More shallowly, you can see that the borehole is deflected in the retrograde direction. And so we are developing an inverse model that is based on the borehole deformation at depth to solve for the slip at depth. And what we're seeing is that in order to match this retrograde tilt, we need to have a slip reduction very close to the surface, and that this is occurring above the observed water table depth. We're also looking at how the slip distribution evolves through time during this creep event. So this is showing now fault parallel displacement on the y-axis versus time. And what's really interesting here is that the inclinometer measurements record a peak displacement at depth prior to the creep meter. So you can see that at day 285, the inclinometer measurements plateau off while the creep meter continues to increase and then accelerates during this rain event. So this is consistent with the idea of a frictionally strong unsaturated layer that's lubricated during the rain event. And it suggests that our fault displacement hazards at the surface may be seasonally dependent. So the final case study is the 2019 Ridgecrest main shock, where we're going to focus on the role of pre-existing structures and rupture orientation. So Ridgecrest is located within the Independence Dike Swarm, which is a Jurassic age tectonic structure in southeastern California. It's comprised of crustal scale dikes that are typically on the order of a few meters in thickness, and they're associated with pervasive dike parallel fracturing of the surrounding granitoids. It's also associated with alteration minerals that are relatively frictionally weak and sometimes infill these surrounding fractures. So we propose that the development of these younger Ridgecrest source faults exploited the pre-existing structures within the Independence Dike Swarm. And we test this by comparing their geometries. So this map on the left is showing the rupture trace with the surface geology and our mapping of the Independence dikes based on remote sensing data. And then on the right is showing a comparison of the spatial variations in the orientations of the dikes compared to the rupture. And so you can see that there is this general agreement between the orientations with this section of the rupture that's rotated about 20 degrees clockwise. And this inherited rupture geometry appears to have strongly controlled the slip distribution. So here you can see the maximum slip zone in pink correlates very closely with the section of the rupture that is rotated. We built finite element models to further test to this geometric sensitivity. So here we're looking at field and geodetic measurements of fault offset compared to models with different assumed fault geometries. And so by approximating it as just a planar structure, we get a very poor fit to the data. But as we improve the fidelity of the modeled fault geometry, we improve the fit to the data. And so that's just a very strong indicator that the slip is sensitive and is responding to these fine scale changes in the rupture orientation. Additionally, the models are very sensitive to the choice of friction, and that fitting the data actually requires frictional values within the range that is consistent with those hydrothermal minerals. So the next slide, we're going to focus way in at this site here from the maximum slip zone. And so the section of the rupture traverses through the China Lake playa, and it is very, very highly localized in these left stepping arrays. The rupture surface often has this stark white appearance with slicken lines. And so we sampled the surface and have been using scanning electron microscopy and microstructural analysis to study the localization processes. And so what we're seeing is that this rupture surface includes this progression from the host carbonate mud to an evaporite mineral called mirabolite, and then to halite. And so this is a very classic evaporite sequence that suggests it formed through evaporation. And I think that the simplest explanation for the sequence is that these fractures are pre-existing. And so that has some pretty significant implications for how we interpret fractures in paleoseismic trenches. Texturally, we see a combination of both brittle and plastic features. So we see that the host mud is being kind of ripped off and boudinaged and entrained into the slip surface, and that the halite is flowing around it. And so previous experiments have shown that at room temperature, in order to get this plastic deformation of halite, you need to have seismic slip velocities associated with a temperature rise and dynamic weakening. So this is very much a work in progress, but we think that this may be giving us kind of a geologic fingerprint of dynamic weakening at Earth's surface during the ridge crust main shock. So just to very briefly wrap up, we see that there are lots of these sort of fine-scaled spatial heterogeneities that lead to really rich spectrum of fault behavior, and that understanding this behavior really requires detailed near-field observations before, during, and after slip events. So thank you, that's it.
All right, thanks a lot, Josie. Thanks for kicking us off. That was really an impressive tour. We have time for a quick question for Josie. We'll get to the general discussion after the talks, but does anybody have a clarifying question or anything? Just raise your hand and we'll get to you. Okay, Yehuda Ben Zion, please ask your question.
Yeah, great talk, Josie. I posted it in the chat box. My question is, did you measure also fault normal deformation in any of those fault zone sites? And if yes, if not, we'll just pass. But if yes, how does the fault normal deformation correlate with damage products, with the amount of shear deformation and some other quantities?
So the brief answer is no. In the work I just presented, I did not measure the fault normal deformation. But I think it's very important in thinking about dilation and dilatation in general. Yes.
Thanks.
All right, and then we have a comment from Christy Rowe. She loves that halite myelinite is seismic, one of the rare earthquake indicators predicted by experiment and confirmed by observation. And then question from Mike Oskin, I'll just read and Josie, you can maybe answer briefly. Is the fault sample a transect into the fault? Mirabulite hydrous sodium sulfite loses water rapidly when exposed into the air, or in the air, to the air.
So yes, it is a transect. So we're looking, like, as you go from the slip surface into, rather I should say the opposite, from the host material into the slip surface, you get that progression from the carbonate mud to the mirabulite to the halite.
All right, there was a hand raised, but it looks like it went away. So in the interest of time, I'm going to push on to our next speaker, who is Alba Rodríguez Padilla. So are you ready, Alba? Yeah, so we're lucky to have Alba presenting to us, and go ahead and present her view. Let's check this is the right way. Yeah, okay. So Alba is a senior PhD student at UC Davis and working on these research topics. And today she's going to talk to us about lessons and questions, the distribution of near field inelastic deformation. Take it away.
Thanks, Ramon and Ashley, for the invitation. And thank you all for being here. I'm really excited to be talking today. I'm excited particularly to be talking between Josie and Chelsea, because they're people that I've looked up to since the beginning of my PhD. So it's particularly exciting to have a talk sandwiched between their contributions. And today I'm going to be reviewing some work, mostly mine, but I've also sprinkled some cool stuff from others that I've been doing, mostly in collaboration with my PhD advisor, Mike Oskin, to understand what the distribution of inelastic deformation in the near field of faults looks like during earthquakes. And just to clarify straight away, when I say inelastic, I mean a point at which a material has yielded. And this yielding can be achieved by many different mechanisms. It may be achieved by fracture, but also folding, rotations, granular flow, anything that exceeds the strength of the material may cause it to yield. And I'm going to be addressing this question by using a range of data from Ridgecrest and other prior Eastern California shear zone events. And our work really starts from this simple motivating question, which is, can we use Rupture maps to say something about the distribution of coseismic inelastic deformation? The answer is obviously yes, because Rupture maps are fracture maps. But let's dig into the details of that a little bit more. Here I'm showing you data from the Landers, Hector Mine, El Mayor, Cucapa, and Ridgecrest earthquakes. These are earthquakes that we mapped at the surface with very, very fine detail, starting with field data that's available for all of these events. And then geodesy has painted a more detailed picture with time as techniques have increased in resolution. And I want to focus particularly in these portions of the Ridgecrest 2019 earthquakes that are mapped in orange here. These were mapped from high resolution aerial imagery and drone imagery. And I want to show you how much detail we can resolve in the texture of the fault zone in the Rupture fabric when we have these high resolution data sets available to us. This was mapped from 2 to 20 centimeter per pixel UAV imagery collected by Ian Pierce following the Ridgecrest earthquakes. And it's just incredible how much of the fault zone complexity we're able to resolve. And from these data sets, we can see that the rupture zone has many, many different textures. Sometimes we have fractures that are related to liquefaction, so they're not even tectonic, like this was on the top left here. The rupture zone is more distributed in some locations. Sometimes it's more localized, like the example that Josie was showing earlier. Sometimes we have cracks that are almost impossible to map because of how widespread they are. They just look like these like ground disturbance. It's hard to pick at discrete cracks. And these set of fractures are generated by different processes. Some of them are generated by the passage of the rupture front. Some of them are generated by the static change. Some of them are generated through liquefaction. And at the moment, we cannot quite tell, other than qualitatively based on shape or angle distribution, we cannot distinguish the processes that give rise to these cracks. But these cracks are telling us that there's this wide range of physics operating in the near field. And to be able to resolve these different physics, we need to be able to look at how these cracks are forming in time. And I think that's something that Rupture can help us with. Another fundamental thing missing in our current picture is that we can't quite tell what mode these fractures are, which is also a fundamental piece of information that's missing. The last thing I want to point out by looking at this figure is how locally heterogeneous these fracture distributions are. It's changing a lot throughout the different sections of the rupture. But despite this heterogeneity, we can compile these distributions together to say something about the general physics of the inelastic deformation zone around the fault. We've done this for the fracture distributions from the El Mayor, Cucapa, Landers, Hector Mine, and Ridgecrest earthquakes. I'm showing you that on the left here. By taking all of the fractures from each of the earthquakes, we've plotted fracture density decay over fault perpendicular distance. And what I want you to notice from this plot is that these populations, these crack decays, are very similar for these different earthquakes. They're all defined by these inverse power laws that extend pretty far away from the fault. These distributions have really long tails. We can see that in these log-log plots, but it's important to not forget that these are still very nonlinear. So most of the information, most of the cracking is contained within the very near field of the fault. It's within a couple hundred meters from the fault. For Ridgecrest, we extended our analysis of the decay of fracture density to also look at other data sets. So here on the right, on the plot on the right, I have LiDAR, field plus, and imagery curves. Those are fracture maps at different resolutions. I've also added the decay in strain intensity that's shown in gray, and the decay in aftershock density, which effectively allows us to see whether our fracture density decays extend to depth. Our fractures at depth or aftershocks also decaying in the same way? And the answer is yes. And combined, these data sets are showing us that there's these widespread decay of inelastic deformation that occurs in a continuum. And this is universal for these Eastern California shears and earthquakes. The next thing we tried to do in one of our studies was take these damage distributions and see whether we could go beyond a geometrical description of the damage zone and also say something about the mechanical properties of the damage zone. This is important because we know that adding fractures or damage to a material changes its properties. And this is one of the fundamental things we try to constrain by looking at this near field deformation. And what we did in our study was, separate for bedrock and sediment, translate our fracture density distributions under some assumptions into decreases in shear rigidity from the fault with distance away. And what we found was that the the shear rigidity decrease in Ridgecrest was about 40% and 20% co-seismically for sediment and bedrock respectively. And these rigidity decrease reduces very, very quickly with distance away from the fault. By the time you're at 100 meters, you've pretty much barely lost any shear rigidity. And this has to do with the very nonlinear decay of fracture density, which causes most of the fractures to be fairly close to the fault, despite the overall widespread pattern. There are other processes, though, that operate within the fault zone on top of fracture, and these are distributed quite differently. I want to start by briefly talking about folding or long wavelength deflections. On the left here, I have a plot of the post-earthquake LiDAR overlaid with the colors of the differential LiDAR from the El Mayor Cucapa earthquake. Blue means down, yellow means up. And you can see that there are these long wavelength deflections that extend away from the fault. These extend kilometers away from the fault. This is about 3 kilometers. That show that the whole hanging wall and footwall are getting warped. We see similar signals for the Ridgecrest earthquakes from the work of Solène and Tuan, who mapped these zones. The width of these lines represents the width of the zone. The zones of distributed deformation that have contributions both from elastic and inelastic processes. And there are these broad zones that are deforming over hundreds to kilometers wavelengths. And an important key point here is that these features are much more distributed than the fracture distributions I showed you earlier. Despite being really widespread, the fracture distributions are quite nonlinear, so the bulk of the fracturing is quite close to the fault. But here we're seeing these signals that span a much broader area, but are also part of the fault zone and part of understanding the physics of deformation in the near field. The last process I want to touch on briefly is block rotations, which are also an important part of fault zones. Here on the left, I have rotations over distance away from the fault for the 2019 Ridgecrest earthquake. This is from the work of Chris Miller, and these are based on the curl of the displacement vector field. So these are measured geodetically. And here on the right, I have work from Ethan Shelov and Mike Oskin measuring these rotations from geologic offsets for faults with under 10 kilometers of total displacement. And you can see that the patterns look quite similar in the co-seismic and the cumulative record. We have rotations that are similarly to the faults, localized somewhat close to the fault, around within by 500 meters away from the fault. Things just look like background noise. But again, this is just another wavelength we need to be thinking about measuring when we're trying to encompass all of the inelastic deformation processes in a fault zone. And the last bit of my time, I want to raise a few outstanding questions and touch on a few ways in which I think RUBZO can help address them. So I think RUBZO can help us understand what are the different processes responsible for the fractures observed. It can help us start classifying fractures in mode and origin better than we can at the moment. In terms of extending beyond the co-seismic period, we still don't know how much of the damage we map is inherited, how much of it is recovered or healed post-seismically. The rigidity reductions we're mapping at the surface are really large. If the crust was deforming that much in every earthquake without any recovery, the crust would be soup after a few earthquakes. So there has to be something happening in between. We don't have information on what's happening quite yet, especially at the resolution at which it's needed. And then we've seen from work by Yehuda that damage can even be produced interseismically. This is seen in background seismicity. So is that something we can capture at the surface to understand in comparison to our very high resolution co-seismic data sets? And last, what is happening to these long wavelength deformation, these long wavelength deflections that are extremely subtle and hard to image, even co-seismically? What's happening to those post-seismically, interseismically? Addressing that needs really high resolution data. And these are just my humble suggestions for things I think RUBZO should try to do since I've been given this platform. So it is great that we're going to have coverage very close to the fault within 100 meters for all of these locations. That is excellent. We need that because these inelastic deformation processes are locally extremely heterogeneous. So to resolve that heterogeneity, we need a lot of near field coverage. But also to be able to say something generalized about it, we need a lot of coverage that we can average, like I showed you from the Ridgecrest and other Eastern California shears and earthquakes. We need coverage on bedrock and sediment because we know they deform quite differently. And we also need coverage of different degrees of geometrical complexity in the fault zone that we can already map pre-deployment of Rupture. I would suggest that we need long wavelength coverage in a few locations to be able to image these processes like the folding, right? Do these come with any geophysical observables that we can image together with them? Currently, the most long wavelength the longest wavelength available in Rupture in the planning is 1800 meters. I think we need to go at least to 3 kilometers in a few places to say more. And last, I just want to make sure that the cameras we're going to have to image the fault zone are angles that enable image differencing and pre-earthquake fault zone mapping so that we can start thinking about these processes during the interseismic period. And with that, I will pass it to the next speaker or to Ramon or Ashley. Thank you.
That was great, Alba. Thanks a lot. Thanks for tackling those, adding those final points. That was really also helpful. So I noticed we have the chat, which people can be using. Raise your hands. But also, if you want to, kind of put the slightly more refined points in, go ahead and get them in that Google Doc so we can really track them. Let's hear just very briefly 1 or 2 questions to Alba. Peter Scher, please go.
Thanks, Ramon, and thanks, Alba. That's fascinating stuff. So many papers show that once you go from that immature, younger faults to more mature, older faults, you have this reduction in the space that experiences inelastic deformation. So are you of the same opinion? And also, kind of that's something we need to think about, right? Because a lot of these observatories are going to cross quite mature and older sections of faults. So just do you agree, and how do you see a possible geometry play out?
So, okay, I think I'm gonna poorly dodge your question, and you can ping me if I haven't answered it sufficiently. So I think, well, one, we're limited by our observational record of earthquakes on mature faults. Like the data quality we have for the Eastern California shear zone events, we haven't had for earthquakes on mature faults in California yet. So it's really hard to say whether these like widespread deformation signals are really going to apply. I would expect deformation to be more localized just on the basis of fault maturity, but I don't think we have the data to say that with confidence yet. I think the other point I want to make is if you take these fracture populations that we're able to image with really high resolution co-seismically and are continuous in space out to 20 kilometers away from the fault, if you take that and downsample the quality of the resolution of the data, then you end up with a zone of localized deformation and a zone with very little fracturing that may look like background. And I think that's how you end up with this. Here's a 200-meter damage zone that may not be like really representative of like how continuous or discrete the damage zone is once you have the data to assess that. So I think in my head, a lot of questions about how these immature faults and mature faults compare needs data. This is a very data poor question. It's part of why we need Rupture.
Awesome. I agree. Thank you.
All right, let's keep pushing, everyone. Thanks for the enthusiasm and the high baud rate here. But let's make sure we hear from Chelsea before we get too in synthetic. So Chelsea Scott's an assistant research professor here at Arizona State University, and she's going to talk to us about fault zone deformation from topography.
Thank you, Ramon, and thank you, Ashley, for the invitation to speak here today. Today, I'm going to show you several types of topography data sets that we can acquire to image fault zones. I'll discuss topographic differencing, briefly the methodology, and then I'll apply this technique to 2 data sets to show you what we can learn from topographic differencing, and then I'll discuss some potential needs for integrating topography into the observatory. So LiDAR is light detection and ranging, and this is a very commonly used data set for imaging tectonic faults. In California, the B4 and EarthScope data sets cover San Andreas and other California faults. And these were both very important community initiatives from about a decade and a half ago, and have been used in a large variety of scientific projects. This figure here on the right shows what a tectonic fault scarp looks like in LiDAR topography data. This is for the 2016 Kumamoto earthquake, where you see this step that stretches across these agricultural fields. And that step is the fault rupture that was produced during the earthquake. Another commonly used type of data is small aerial system or drone-derived topography. So these data sets are typically very high resolution. So they often have over 100 points per meter squared, and they include color. They are often collected by small groups of researchers. So they provide opportunity for students and researchers to go into the field. For example, this data set here along the southern San Andreas fault. For this data set, Mike Bunz and I collected this in about 3.5 days, 40 kilometers along, just before the pandemic. And so here's what this type of data looks like. Pay attention to the scale bar. This is just 100 meters. And we can see very nicely the fault scarp produced by the southern San Andreas fault. So when we have topography data from before and after an earthquake, we can do topographic differencing. This picture on the right shows the results of 3D topographic differencing, where the arrows with the pink ellipses represent the horizontal coseismic deformation along with the uncertainty, and the colored dots represent the horizontal or the vertical deformation. And so this high resolution topography offers both high resolution measurements of displacement on and near the fault. This is in contrast to GPS, which has a much lower spatial resolution. And in contrast to INSAR, conventional INSAR, these displacements do not decorrelate along the fault. And so they offer important observations of near fault deformation. So this demonstrates how 3D topographic differencing works. It's done with a windowed implementation of the iterative closest point algorithm. And so in this algorithm, we take subsets of the pre and post topography and align them using a rigid body transformation. And so in the figure, in this video here on the right, you see that the blue or pre-earthquake topography is iteratively moved closer and is aligned with the post-earthquake topography. And it's that full motion that it takes that is then assumed to be the coseismic deformation at that area. So I'll now discuss what these data sets can show us about earthquakes and faults. So here are the 3D topographic differencing results from the 2016 magnitude 7 Kumamoto earthquake. And so the arrows represent the sense of motion. And I'd like to discuss the top plot here. You see in black are the faults that ruptured in the earthquake. And there's this really sharp change in displacement across the fault, and that's indicative of the coseismic slip during the earthquake. And so these differencing maps can be used for a variety of applications, including calculating the coseismic displacement or slip, looking at fault deformation, strain, and in slip inversions. And I'll discuss the latter two. So here is a map of the coseismic strain. In particular, this is looking at the first invariant of the 2D strain tensor. So that's the horizontal area change. And then in red are those faults. And so you see that this area of experienced tectonic strain during the earthquake extends beyond the fault is consistent with what we saw earlier today. We can use these maps to look at the area that experienced inelastic deformation, or where the elastic strain limit was exceeded, and that's outlined in the black. And so we do see over 100 meters of these areas that experienced inelastic deformation that bound the fault. Topographic differencing can also be used in joint inversions. So this is the result of a joint distributed slip inversion with the 3D topographic differencing, optical correlation, and INSAR. And so here we're looking head on at the fault, and you can see the amount of coseismic slip. And so what do we gain for using topographic differencing? First, based on the high resolution near fault displacements, we can add complexity to the shallow fault geometry. And so there are subtle bends in the fault geometry just below the surface. And we can also resolve more shallow slip than near field displacements, or than far field displacements, for example, from INSAR or optical correlation, as well as from strong motion and teleseismic data. Can also quantify the impact of LiDAR differencing in these joint inversions. So this figure here, again, shows the fault plane, and each patch is colored by the data set that has the largest impact on the resolved slip. These black arrows bracket the spatial extent of the LiDAR data. As you can see in the area of the LiDAR data, the LiDAR or topographic differencing adds key constraints to that shallow fault slip. And those results are summarized here. This shows depth versus resolving power. And we see that the LiDAR data has the greatest resolving power in the shallow crust, with decreasing resolving power with depth, and INSAR shows this opposite relationship. This suggests that going forward to really resolve slip throughout the seismogenic crust, it's important to add LiDAR and topographic differencing to these slip inversions. We're now going to go to the creeping section of the central San Andreas fault, which is shown here. And I've colored the fault, the central San Andreas fault here, as well as the Calaveras fault. Those are both colored according to the slip rate resolved from topographic differencing. I will now zoom in here to Mustang Ridge. This area has been the focus of the several USGS scientists who've mapped both in the field and from LiDAR data, and they've produced this map of the area. And in particular, we see that the San Andreas fault here, which is shown in these black and red lines, makes this major step to the right in this releasing bend. This deformation is also accommodated here along several kilometers of en echelon during an en echelon fracture zone. Now, the topographic differencing results are generally consistent, but they add an important insight. So here are those topographic differencing results. And like we saw before, we see this really sharp discontinuity across the fault, and that reflects the change in displacement along the creeping fault. But importantly, the topographic differencing shows that the deformation is active here. This is where the fault makes that step over. And that's several kilometers away along strike from the fault that is most prominent in the geomorphology. So we can use topographic differencing along with detailed fault mapping to look at fault zone evolution over the tens of thousands of year timescale. And these results also have important implications for fault displacement hazard, as we can, with these mapping and differencing, can well locate the active fault. So in summary, I would like to propose some needs for using topographic differencing in the observatory. So to summarize, we can use topography and topographic differencing to map faults based on the landscape geomorphology. We can measure 3D and vertical change to the co-seismic and post-seismic deformation. And I showed you a variety of applications of that work. And so for doing topographic differencing, there's several important needs. For the pre-event topography, we need to have airborne LiDAR, ideally with a fairly large aperture to capture slip in the deeper portions of the seismogenic zone. The advantage of airborne LiDAR is it's a fairly advanced technology, so there are established quality levels. So for these data sets, we know well what we're getting, and that if they have a good enough quality to answer the questions that we're after. The other important data set is drone-derived topography. These offer very high resolution, but one challenge is that they do require very good georeferencing, and this is often challenging to get correct. And for post-event topography, it's important to collect that first data set as soon as possible following the earthquake, and then to have ideally monthly acquisitions or so to capture the post-seismic deformation. Thank you.
All right, thank you very much, Chelsea. Let's see, we got a couple comments. Let's have maybe a quick question directed to Chelsea and a comment. Just one thing I'll read first. Mike Oskin says, airborne INSAR is another tool to measure the near-field post-seismic deformation. So we saw that UAV SAR, for example, for El Mayor Cucupa was quite valuable.
Yes.
Please, Yehuda Ben Zion.
Yeah, great talk, Chelsea. Thank you. I'm just wondering, maybe you said it, did you try to measure time-dependent topographic differencing? Did you work on this evolution in time? Not just, in particular, post-seismic, such as Ridgecrest, but even inter-seismic. And specifically around lacked faults. I know the cripping section is very, very important, but it's also very spatial, and everything is very localized. But around lacked section, Alba in her talk emphasized the topographic warping, and I'm wondering if you measured this.
Yes, so for example, you can see here, looking at these maps for the Kumamoto earthquake, that there is significant off-fault deformation, particularly visible in the vertical displacement. And so, yes, topographic differencing can certainly be used to capture warping and quantify the off-fault deformation. And then your question was asking about time-dependent deformation.
Yes, how does this evolve in time?
Very good question. The general challenge is that there have not been sufficient data to look at that question with topography.
Would cameras be useful there, or we need to fly drones, or we need to look from above? How do you suggest what should we measure?
So a challenge is that these data do generally have higher noise than INSAR. And so it's, for example, to measure co-seismic and then post-seismic deformation with these techniques to get that 3D resolution, then it would be important to get frequent acquisitions following the earthquake to, one, distinguish between those two, and then to have sufficient amplitude of post-seismic deformation to be able to resolve something with these data sets.
All right. let me just do a quick time check here. So we've got 34 minutes to go in this session. And so got a couple questions queued up there, which I'll turn to you guys in just a moment. I want to remind everyone about the Google Docs to try to put in some ideas there, help us capture them. Raise your hand, sort of come up to the virtual mic for your remarks by raising your hand. And then just remember the questions. So I'm just going to read these one more time, and then we'll go to the people with questions. As science questions, let's think broadly. Remember, we're community engagement for a future rupture fault zone observatory. So what do we see geologically and geomorphically when we look across fault zones? What are the products of that deformation, both in, sort of two-dimensional views, map or cross-section, and also volumetrically? What are the implications of those products? What's the time variability of the signals? How can we observe these using the purpose-built observatory? What do we need in the observatory? And then remember, what are those signals that we can help us answer questions? What are the properties of the observatory that help us measure those signals? And how do we involve the next generation? How do we engage more with the community? So that's just a reminder. Let's go to Ben Brooks, please.
Yehuda, you had asked about measuring interseismic deformation with LiDAR and laser scanning and topographic differencing, and the rates of interseismic deformation tend to be a little too low to measure with those techniques at the sort of centimeter scale. So it's very difficult to measure interseismic deformation with LiDAR.
Right. Let's go to Alba. Question from you.
I was gonna add to what Chelsea and Ben have said. So first, from the co-seismic point of view, I think it's important to keep in mind that the signals we're interested in are best characterized by different data sets. So for example, the fractures are essentially invisible in the LiDAR data because they do not have enough vertical displacement to be visible in LiDAR. But the deflections are best captured with the LiDAR because they're maximizing the direction that LiDAR captures best. So we need these different data sets to capture different aspects of the fault zone. In terms of characterizing interseismic deformation, one of the things we're missing with LiDAR is just not dense enough in time, but we can do that with imagery. And if we have really high resolution imagery close to the fault, we can generate time series and difference that. And I think even if the displacements are really small over long time, especially if roofs are deployed for a long time, we should be able to extract some interseismic deformation from that.
Yeah, thank you. It seems like from a technology standpoint, it'd be quite interesting. We know from image correlation methods, you sometimes can go at 10% of the pixel resolution to compute differences. So, could we push to that super fine scale to pick up, sort of centimeter differencing or even finer? We probably would start to pick up other environmental changes like expansion and sort of deflation of the volume due to saturation, which was kind of a point that Josie implied. Okay, so let's see, we've got still some time. Let's broaden the discussion, but also just throw out an idea. Hi, Kate, please, do you want to say something?
Yeah, I this is broadening the discussion, and sorry, I didn't pay attention to the sequence of discussion, but one of the things when I look at the rough zone observatory concept is that we don't seem to be, and it's a disconnect between this near fault work and these vast data sets of VS30 that are out there. We're sort of not using and thinking about ways, or I haven't seen it yet. Maybe someone is out there and they can correct me on this, but how we can leverage the type of information that the speakers are collecting to broaden it, because it's one thing to get, to sit here and wait for that one rupture, but then we also want to propagate that information out. And I think there's not a lot of communication between kind of the VS30 or the geotechnical layer, all the things we call the near surface, and a big chunk of data that already exists in that field, but is really different from the kind of information that we've been collecting so far in these near near fault studies. So if anyone has insight or ideas in that direction, I think that would be really cool to see, because that would allow us to leverage, how is the LA basin going to respond, not just, say the next one's actually on the Newport Inglewood or something like that. Don't think that.
So let me just ask clarification. It's not really my expertise, but so could you do like delta VS30, like across the fault zone? So you do it once and then an event occurs and do it again and again and watch the evolution of those properties?
That's right. Or even, there's a big push right now to do much higher resolution VS30 studies for where we have our seismic stations. And I think that's becoming kind of standard practice. But do we also need to be doing more of a field deployment of those types of measurements so that we can understand basically, I think it's a pretty quick and dirty way what the near surface properties are, rather than, otherwise we're dependent on our geomorphic maps, which are really great, but they don't really get at the three-dimensional qualities that people are investigating now.
Thanks, Kate. Yeah, everyone, just that's wonderful. Keep raising your hands, because then you move to the top of the Zoom screen so we don't miss you. Please, Yehuda.
Yeah, I just want to respond briefly to Kate's point. So this is a great, you bring a very important issue, Kate. So we need many kinds of data, right? So this Rupture Observatory aims to fill critical missing data right around the fault zone. But a big part of our effort would be to integrate. This is kind of part of the plan, to integrate whatever we measure near and around the faults with, for example, more regional data sets. You mentioned VS30, this would be one. What do we see? And so that we will work on integrating it, and as well as the regional velocity models and regional community geodetic models, etc. So yeah, Ramon had a point. Maybe we could make repeating measurements, VS30 on all of those sites every year or so, as measurements continue.
Yeah. Okay, I'm going to read a couple of chats, but please raise your hands in the Zoom just so I can identify you. There was a comment from Douglas Schmidt. The LiDAR people are claiming the ability to make repeat measurements on timescales that one could measure surface wave displacement propagating. No idea how one would implement this to study fast deformations during an event, given that the reference is likely moving too, but something to think about. So, we want to have a picture or a video of the rupture front coming by, but could we be laser scanning it at the same time? Anybody want to pick that one up? It's a cool idea. Okay, well, think about your comments there. Let me read another chat. William Harbert says, great talk, no response. You might apply empirical Bayesian kriging to estimate a higher resolution, could be interesting. Yeah, so, there's some data science to be done here as part of as we think about how to make these observations and get the most out of them. Let's see, anyone? Frank Vernon, you have your mic open. You want to say something?
Yeah, I was going to say one of the things that would be possible to do, responding to Douglas Schmidt, is to think about housing local drones at each of the subarrays, and then anytime you have anything that triggers any of the earthquake warning systems, you launch them automatically. And that way you could do both the LiDAR as well as optical imagery simultaneously from a platform that's decoupled from the ground, which is, it saves a lot of, will give us a whole new perspective on things. And it wouldn't be, that's something that's within the technological capabilities of today even. So if we thought about it and planned it in advance and made it work. So that was my comment.
Yeah, I like it. I think the robotic observations are going to be key. And I can imagine, I see this little hemispherical dome open up, like you get the warning and then, the SUS.
Right, but I mean, when you figure about the seismic wave propagation, if you have, even if it's, already shaking one array, by the time of propagation next one, you have plenty of time to get something going.
Exactly, and watch it from above. And then you your reference frame is basically a differential GPS reference frame in the air.
Yep.
So let's go to Ben Brooks.
Yeah, ground-based radar is a much more apt technique for these small deformations. It's a sub-millimeter technique. It's been shown, you know, I think people are familiar with that. And we had talked about UAV SAR, which of course is really high resolution, but ground-based radar is really the most appropriate technique for a lot of these near-field small displacements.
Yeah, cool. Thanks. Let's hear Douglas Schmidt. You
okay?
ready?
Yeah, actually, sorry, I had my mic on. It's actually Doug Schmidt, but that's what my it's okay.
Go ahead.
For the people who know me. Anyways, yeah, no, there's interesting comments. And the reason I brought that up, I was just at the SEG conference and they were talking about near surface type more for monitoring and there was a company apparently claiming they could do the LiDAR in very short time. So, but another point is that there's lots of fiber optic technology now that could be different kinds of it that could give us both, say, short-term strains, relatively high resolution, plus repeatable kind of strain measurements that a person could dig in near the faults. And maybe that, I haven't read this paper by everyone, maybe that's already in there, but that's just some thoughts where things are going and could be implemented and continuously monitored.
Yeah, thanks a lot, Doug. That's great. And yeah, that connection SEG and these geophysical tools and communities are really important. We have Yehuda is queued up, but I want to push everyone. Let's hear from some people who haven't spoken yet, especially some of our early career colleagues. Don't be shy. Anything sounds good out here. This is the time to toss out those naive ideas that end up being really awesome and want to take them in these directions. Please, Yehuda.
Yeah, I just want to make the point that we have two cameras currently looking at the San Jacinto fault zone in the trifurcation area on the damage zone for several years. And we plan to have cameras in each of the Ravzo arrays. So if anyone would like to practice on doing some processing to these images that are coming from the camera, looking at the daily changes, seasonal changes, maybe tectonic changes, send an email to me and or Frank Vernon, and we'll give you access to the data. This is just measuring. We have images at some frequency. We can increase the frequency of acquisition as well. So if you want to practice, let us know.
Great, thank you. How about some more? Frank, you want to say something?
No, I think that was, again, say that Yehuda has mentioned the images that we are already taking. The sample rate's currently once a minute, and we're working on upping it to certainly once every 10 seconds, and can push it higher. I have a little bit of a solar power problem, so that sometimes at night we don't get it all the way through the night, but still better than nothing, and we'll continue to try and improve that system.
Right. Oh, thank you. We had a couple of items on the chat. One, just a point from Chelsea Scott, important not to underestimate the importance of good georeferencing to resolve small displacements. So we need to have some careful geodesy there. And
I was
then
in reference to getting these drones up quickly.
Right. Thank you.
But would that mean that you're just talking about putting markers, the reference markers in the field of view, so that you could actually, tag specific places, or what are you thinking?
Yeah, so you could use very dense markers. I have done field work collecting drone data for differencing, and it didn't work. Along the central San Andreas Fault, because basically marker every 250 meters was just not dense enough to get good enough georeferencing to capture a decade of the creeping fault. And so it's technical, but it's really important to have probably a good connection to a ground-based differential GPS, and to explore in advance the technical needs to get the quality and uncertainty needed to really, if you want to have a drone flying, frequently, what do you need to really use that data for the georeferencing?
Thanks, Chelsea. Before I get to Peter, I wanted to put out this question from Art Frankel. Do people think about how these variations in near surface fault properties and geometry generate high frequency ground motions? So from the seismologists out there, what are we getting from failure of those shallow materials seismologically or seismically?
Yeah, I guess to enlarge on that question.
Go ahead, Art.
Yeah, I was thinking about, do some of these things extend to depth, particularly like differences in geological materials. And, the more we look at strong ground motions, we see that the high frequency damaging ground motions come from very localized portions of the fault. Of course, usually it's at deeper depths, but I think, some studies show this stuff generated at shallow depths too. So it would be good in advance if you could have, small arrays of seismometers around some of these differences in fault behavior or discontinuities in strike and things like that, to see if these features did generate strong ground motions during an earthquake.
Thanks, Art.
I want to respond briefly to Art. So we are hoping to measure all of this, Art. This is why we need very dense measurements right around the fault to look at the high frequencies, strong ground motion, and then to correlate it with whatever it correlates with.
Good. That was, thanks for that. Before I call on Peter, let's get some more people up there to the microphone who haven't spoken yet. Please don't be shy. Let's we still have time. Let's get some more ideas, more questions, technical, science, people, how do we engage more people? How are we going to do this and teach about it and train about it? Peter.
Yeah, actually, just to Art's comment quickly, I'd welcome him to join next week's call, because it's going to be one of the foci of that call, just to figure out what the complexity is, especially near these faults. But sorry, there was a break in chat, and I was still curious about what Kate mentioned. So just to clarify, so Kate, do you mean by your point that you would like to see the seismic and geodetic networks that exist right now densified away from the faults also, in addition to having more sensors near the fault? Is that what you were getting at? If Kate is still on the call, is that what you meant? Sorry.
Yeah, she's here.
Yeah, I'm here. Sorry, I don't see where my raised hand is there. So pop up to the front.
Nice.
No, that wasn't specific. No, I was trying to think about how we can use, there's this dense, the VS30 measurements out there are prolific, and they're relatively easy to measure, and it would allow us to leverage information that we have about the fault that actually does go to these other places. And because it's non-invasive and quick to do and covers, a wide range of settings, like, I think the work that Josie's doing is super awesome, but I also want to know, like, well, how does a crusty alluvial fan respond as opposed to a playa? And by using non-invasive geotechnical techniques, we can try to do that, at least in an informed way. And so my hope is for a little more communication between the geologists that have, been getting dirty in the trenches and looking at the specifics of these very site-specific locations, and broadening that information and sort of building off the VS30 data sets or other types of data sets out there. I mean, maybe we just need to be, it doesn't have to be VS30 per se. There's lots of new ways of doing that, big nodal arrays and all that kind of stuff. So that's what I'm trying to understand, if we can make some headway there that allows us to broaden. If we do get specific measurements for one, these data are so rare, that one extra earthquake we capture, how do we then say, oh, well, then this is how other areas might respond?
Thanks, you guys. That was great. And yeah, maybe some of that will be picked up next week. But yeah, I love crusty alluvial fans. Let's hear Josie.
Yeah, sorry, took me a while to find the raise hand. I wanted to respond to Art's comment. Yeah, I think that the connection between some of these very near surface observations and the near field ground motions is really important and exciting, and something that we have a pretty serious observation gap for right now, that we just haven't been recording the near field ground motions. But so for instance, for the Hector Mine earthquake, Andy Michael made some really interesting kind of geologic observations that for these longer pieces of the rupture that look a lot like the playa section from Ridgecrest, he was looking at like the displacement of pebbles and finding that they weren't displaced for these longer segments, but they were for the more distributed fracturing, like what Alba was showing. And so I think that, that is an indicator that there are some, differences in the kind of high frequency ground motions related to these very fine scale structural changes. And then there's also work that's been done by like Daniel Roten and Kim Olson, looking at how fault zone plasticity can influence the resultant ground motion. So I think that link between the very fine scale fault structure and rheology to the ground motions is super important, both scientifically and from a hazard standpoint, and is an area where I think REFSO could really make like a big contribution.
Yeah, that's great. I like the idea of those natural seismometers of flipped rocks and pebbles that are moving in the near field and what they might say. Let's go to, it looks like, just want to interrupt here. Casey wants to poll people who maybe haven't done the poll already. It just popped up. Is that right?
Yeah, sorry to disrupt. Just wanted to catch people before they left for other meetings, but please keep the discussion going. So I'll leave it open until the end of the session. Thanks.
Okay, thank you.
But just note that there is a comment or a question here from Joanne Stock above that in the chat.
Oh yeah. Let me get to Joanne. I think Joanne, I saw Nick Barth's question appeared before your chat did. So hopefully that's okay. But then I'll go to you, Joanne. But Nick, go ahead.
Well, yeah, just to add to the idea of the automatically deployed drones, I was thinking a high frame rate camera would also be potentially really interesting if you can catch the rupture evolution in action. So it's kind of one thing I was thinking about. And then presumably if you have an observatory site doing an old school concrete wall, across perpendicular to the fault would probably still be very worthwhile despite all these much fancier techniques we have. And kind of related to that, I was kind of thinking you could have masses and rocks and disks of like known size and mass to see how they respond. And so, alluding to, I think Josie mentioned the pebbles, I've certainly heard of like flipped rocks that flip like pancakes and in several different ruptures. And so kind of having like a series of reference weights sitting on the landscape, and related to that, maybe some mock-up of precariously balanced rocks that have different geometries would potentially be really worthwhile in the long run.
Yeah,
and easy and cheap.
I love that, some actual physical experiments in the field. Let's turn to on this question of watching what happens. Joanne Stock asks, what sensors can fly or image through the dust clouds that are raised by the shaking? So I guess, the complex shaking, might start producing dust even before the rupture gets there. Now, maybe that's where the radar would come in. I don't know. Do you want to ask a little bit more, Joanne, to elaborate?
I was just wondering if there's some innovative technology we should be thinking about. Because of course, like El Maricucapa would be a good example where there was a trail of dust that was observed, right? That was formed as the rupture propagated, but then all the aftershocks kept shaking things loose and producing more dust here and there. And so I just thought it should be something to try to look for, cool new techniques that could maybe help us with that.
Yeah. I like that. That'd be kind of bummer. You have all these drones flying, just looking at dust. They wouldn't even see the hidden.
Well, I'm not sure
from
they could, I mean, that's the question, like, can they fly safely if there's dust?
I think, but yeah, it's
Okay.
a big good question. But they might not see anything, as you say.
Well,
Anybody
hopefully the
wanna-
dust would settle, but
after some time.
yeah.
Anybody want to take that? Any imagers out there? Thoughts? Like, I mean, radar goes through dust, right?
Yeah, radar, I think, would go through dust. But maybe not optical wavelengths. I mean, yeah. But that's where I think someone who's like very knowledgeable about all those different kinds of sensors maybe could help us with that.
Yeah. That's great. Thank you. Okay, we got 9 minutes, so let's hear from some other people who haven't spoken. Don't be afraid. Still plenty of you out there. Alba, go ahead.
Yeah, I am curious what information numerical modelers are lacking when they're modeling rupture, things like rupture propagation. What information do they need from RUVZO to incorporate into models? Like, what are the gaps and what can we observationalists do to fill in those gaps? So my question is to call other people to answer it.
Yeah, anybody want to take that on? What don't we know? Or if we knew something, how would that help us? Yehuda, you want to take that one?
I can respond very briefly, and then I got to run. So the models do not incorporate many aspects of the near fault zone environments, starting with variations of material properties, elastic moduli. They typically do not include volumetric deformations, are limited just to pre-existing surfaces rather than dealing with volumes of the type that you showed that are activated, Alba. So if we can quantify better the volumes involved, the changes of elastic properties, of course, we would need to understand how things change with depth as well. So Chelsea showed an interesting results on resolving power with depths. All of these measurements can be included in fault zone models, and then the models will predict new signals that the geologists can go and look for. You know, there's this very good potential feedback loop between the modeling and this. So there are lots of things. The models right now are fairly simple, Alba, and just including the volumetric aspect of the fault zone, both in terms of the volume that it occupies and the variations across this volume will make a big difference to the simulated results.
Thanks, Yehuda. Yeah, that sounds very good. We have a question that is really interesting from Ashley Griffith. So we've talked a lot about displacements and fracturing and velocity fields, but what about other properties like heat flow or gas flow, gas chromatography? Does anybody want to bite on that one? Yeah, it'd be great to have gas sensors, soil flux accumulation chambers constantly monitoring. Lauro Chiaraluce.
Yes, from Europe.
Thanks for joining us. I know it's a little late.
No, thank you for doing this, for organizing this. I've been somehow linked by Yehuda that I contacted after the opinion paper. And so I'm very happy because in Europe, we have a near fault observatory community from at least from about 6-8 years within the EPOS initiative, European Plate Observing System. I mean, the idea there is it's a little bit different. We are not exactly, we didn't build this infrastructure located in different areas in Europe with different kinematic, velocity field from centimeters to millimeters. So, we were not exactly waiting for a large rupture. We just wanted at the beginning to increase the resolution of our day-by-day data that we use for our day-by-day research. And So we have actually we have a multidisciplinary monitoring infrastructure. So we have radon and CO2 measuring systems permanent, because in some of the sites we have these huge CO2 fluxes, and not necessarily or not clearly with the volcanic origins or mantle origin. So one idea, for example, for us, one interesting thing is to look at the connection between fluids and deformation and strain. That's why we deployed strain meters, for example, in shallow boreals. And, and essentially, we are very interesting also in increasing the resolution of our observations. So the idea is also to look at smaller seismic sequences and see ideally to look also for, what happened before even a small magnitude main shock. Let's say if there are some precursory or some statistically signals that statistically repeat before the occurrence of a small magnitude events, because when you have, in terms of, for example, of seismic catalogs, completeness of about 0 point something, a magnitude 3.5 is a main shock. So we can see seismicity migration, we can see diffusion processes, and so on. And sometimes we also see a seismic deformation at a very local scale. So, I mean, the idea is pretty similar, I think. As I said, our infrastructure deployed in Greece, in Italy, in Turkey are not necessarily waiting for large ruptures to increase the infrastructure and the density of the monitoring networks, are essentially multidisciplinary. And so I think there is a lot of things going on in common. So I'm looking forward to see your future steps, let's say.
Thanks. Yeah, your experience is super valuable. We're very close to the end, so the next set of remarks will need to be brief. Let's go with Roger first.
Yes, just a comment with Ben Brooks and Josie. We have in fact got gas monitors at 10 of the USGS creep meters along the creeping zone in Northern and Southern California. And we have started measuring strain in the flanks of the fault, in addition to the dilation across the fault. And these really are our pilot experiments. From the initial results, I think I would like to see gas monitors at every creep meter, and in the proposed experiment, I think it would be useful to stress that one needs gas monitoring. By the way, we're measuring once per minute CO2 and hydrogen and methane and so on. We'd like to see measurements both in the fault zone and in the flanks of the fault zone, so we can distinguish gases coming up the fault from those that are of biological origin contiguous with the fault.
Thanks, Roger. That's great. Are you done? Was that your main point? Okay, yep. Thanks. Josie, briefly.
Briefly, something we are lacking right now are true coseismic displacement measures. So basically, there's a logistical challenge of getting to an earthquake rupture after it happens. And we don't respond to most within 12 to 24 hours, during which you can have a lot of post-seismic afterslip if there's going to be that. And that will contaminate what we view as coseismic if we don't have those kind of immediate on-fault coseismic measurements. So that's all.
That's very important. Ben, briefly.
Piggybacking on both Roger and Josie's comments, it seems like an elephant in the room that we've talked about before is that proposing a near fault observatory to capture an earthquake has a very small probability of actually observing an earthquake. of any significance. So there might be measurements that are useful regardless, but certainly a lot of the geodetic stuff won't necessarily be useful in a magnitude, 4 or 5 event. And so the question comes up then is, how pertinent are creeping faults? What can we learn about creeping faults in terms of process that might teach us about faults that slip co-seismically? And I think it's something that needs to be considered seriously by this community.
I agree. I thought Yehuda said, oh, the creeping section is special, but it's actually special because it's doing something that we can.
There's a signal.
Yeah.
There's a signal.
Yeah. So Alba, final comment briefly.
Well, that's a lot of responsibility. I just wanted to say that I think even if we don't get to capture a large earthquake, there's so much that we're still missing from the interseismic period. We know that the faults move, that they respond to tectonic and climatic loading. We know there's all of these like fine adjustments on the fault, and understanding what's happening interseismically is going to give us information about how the big earthquake will eventually start, even if we do not get that earthquake captured within the lifetime of the array. So I think there's a lot of value to having those interseismic observations in there.
Yeah, and just even planning this will drive a lot of science to think about what to do and how to measure it. Okay, I want to bring this meeting to a close with our gratitude first to our speakers. Thank you guys very much for really stimulating and really nice, interesting talks. Want to thank Casey Alderhold for supervising us all and making this go smoothly. And I want to wish us all the best as far as we move forward with this project, and invite everyone to stay as involved as you can. Try to attend the other sessions so that you can see all the different perspectives and see cross-cutting ideas. Casey has the, where do we go from here? So please take a note of those URLs and these next steps. And with that, I'll give the final word to Ashley Griffith, our co-convener.
Thanks, Ramon, but I think that Casey has the final word here.
Oh, right.
No worries.
Sorry, go ahead, Casey. Thanks, everyone.
Thank you both so much, Ashley and Ramon, for organizing. Thank you to Josie, Alba, and Chelsea for your presentations, and then to all attendees for your participation in this session. If you are interested in future community near fall observatory breakout sessions and other events, including next week's, please check out the website and the link provided and go ahead and register for those. Thanks so much for joining.